So now, I mean, just for your information, that the estimator what you have used, this B ordinary least square estimator, that is a very good estimator. That is unbiased, its covariance matrix is this, its variance can be estimated by this, and the covariance matrix can be estimated by this. This is just for your information. I don't want to scare any one of you, but I just wanted to inform you that when you are trying to know the value of the parameter, you cannot do it blindly. You have to evolve a proper formula in statistics, and then you also have to ensure that the formula which you have obtained is really good or bad. So these are some properties of those estimators that will ensure that the values which you have obtained here, like these things for the model here, these values, they are going to give you a good value. The good is in the statistical sense, right? So, and then, yeah, means if you want to find out the covariance matrix of your residuals, the estimated, etc., etc. So this is just for your information. Now I come to another aspect, that a testing of hypothesis. So when you are trying to find out the model on the basis of given sample of data, you would always like to make sure that whether this model is actually good or bad, it is really conforming to your requirements or not. So we have different types of aspects. So first aspect is how to conduct that test of hypothesis on this regression coefficients. Why? Because you see, if you try to see what are you trying to do, you are trying to find out the value of beta 0, beta 1, beta 2, etc. These are the values which are existing in the universe, and you are trying to estimate them only on the basis of a small sample of 20 observation or 30 observation. We are not actually God. The real value of beta 0, beta 1, etc., that is only with the God. But surely God is not going to give it to us. Right. So we try to conduct the test of hypothesis, and this test of hypothesis will give you different types of information. Even you can judge whether the obtained model is good or bad, and you can also judge whether the variables which you have considered, are they really educate good or bad. So how to conduct this test of hypothesis? For example, if I say here, suppose if I want to test the null hypothesis that H naught beta j equal to 0. Well, I'm assuming here that you have a fair idea of the test of hypothesis. You're right, I'm assuming here. And you want to test here H1 beta j is not equal to 0. So definitely if you accept this null hypothesis, that means beta j is equal to 0. That means the beta j is the rate of beta j is the interpretation of beta j is the rate of change in the average value of y with respect to xj. That means when there is a unit change in the value of the jth explanatory variable, then how much the average value of y is going to change. So surely when you are trying to say that beta j equal to 0 is accepted, that means in the population beta j is equal to 0, which means the rate of change in the average value of y with respect to jth independent variable is very small, close to 0 ideally. So when there is a variable which is not really going to change your outcome, will you call it as effective variable or a good variable? Surely not. You will say, no, this variable is out of use, and this variable should not be in the model. So this is exactly what we are trying to do. So suppose we are considering this model here with 3 variables, and suppose S naught beta 2 equal to 0 is accepted. Now my revised model will become here x1 beta 1 plus x2 into beta 2 equal to 0 plus x3 beta 3 plus epsilon. So this term will become 0, and you have here a revised model here x1 beta 1 plus x3 beta 3. So obviously now the question comes here, how are you going to determine whether H naught beta j equal to 0 is accepted or rejected? Right. So now for this, actually, if we try to use the t statistics and we try to obtain the standard error based on that. That is the job of a statistician. So I'm not going into those details, but we try to create a t statistics here, which is here like this: bj upon standard error of bj. This follows a t distribution with n minus k minus 1 degrees of freedom. Well, I'm writing here, it is something like here n minus k plus 1. K plus 1 because there are k independent variable and one uh, intercept term. So you have to be careful that how you are trying to count that total number of variables. So anyway, so this is not your job that how to obtain this thing, but surely when you are trying to do the software analysis, then this value is going to be there, and that is why I had to tell you that this is the value which you are going to obtain by software. So obviously the rule after this is very simple, that reject H naught uh, against the null alternative hypothesis at alpha level of significance if p value is less than alpha, or the classical way is you try to calculate get the tabulated value of a, and you get here the tabulated value from that table, and when you try to conduct the test of hypothesis. So what I'm trying to say here, I'm not going into the details of test of hypothesis, but I'm simply saying that you conduct the test of hypothesis and take a conclusion. And if the hypothesis is accepted or not, that depends on the given data. Right. So now if I try to take the same example here, and if I try to see the results about the test of hypothesis, then definitely I would say here that we have a command here, summary, that can be used to get all such data. So I will say as summary, and the same formula which I have used for the fitting of the model. So I will write down here summary is equal to summary like this one. Right. So now let us try to understand what is really happening here. Right. Don't get confused here at this moment. I'm promising you this will look very complicated. What is this? But let me try to show you one by one what is really happening. So let us first try to look at here. Do you understand what is this thing? This is here intercept term x1, x2, x3. So if you try to see here, this is nothing, but this is the same value which you have obtained here. You can see here, this is the same value. So now all the information is here given here in a different way, different format, so that you understand how these values are obtained here. Now, these are here the standard error. Means obviously when you are trying to estimate the unknown beta 0, beta 1, beta 2, beta 3, so they will have some variability also. So here I have given you here a formula, which is here. This is going to give you this value here. Well, you don't have to compute it manually. It will be done by the software. So this is trying to give you here the value of the standard error of intercept beta 1, beta 2, beta 3. Right. So obviously if these values are small, that means your estimator is good, because standard error means the variability. Okay. And then after this, you can see here, this is here t value. So t values are just the same thing which you have written here. Right. So now these are the value of the t statistics for intercept term, for x1, x2, and x3, for beta 1, beta 2, beta 3 actually. So now these are these values, and these are here the p values. So you can see here that all this, if you try to take here alpha is equal to 5% level of significance, which is the most common thing, then you can see here all these values are much smaller than alpha is equal to 0.05. So that means all this hypothesis h naught beta naught equal to 0, h naught beta 1 equal to 0, h naught beta 2 equal to 0, h naught beta 3 equal to 0, they all are rejected. That means all the variables which you have taken here, x1, x2, x3, they all are important and they should remain in the model. So this is how this part is now covered. Now you understand what is there in this part of this horoscope. Beside those things, I can also show you here. Let me try to clear this screen so that you can see it more clearly here. Right. So now you already have done this part you understand. So let me try to cross it here. So at the end, you cannot complain that you have not covered this part. Okay. Now, if you try to see here, this is here residuals, minimum, first quartile, 1Q, median, third quartile, maximum. So here you can see here you have found the values of residuals. You can see here, these are first value, second value, up to here, 20 value. So what it is trying to do, these are the 20 values of the residuals corresponding to this 20 observations, and this observation is simply trying to give you the minimum value out of these residuals, maximum value out of these residuals, the first quartile, second quartile, and third quartile of this 20 values. So they are trying to give you an idea of the distribution of the random errors. Why? Because you have assumed that your random error is following a normal distribution. So if you believe that it is normal, so then the median should be equal to the mean, and so on. So this will give you a fair idea about the distribution of the residuals, and if there is a lot of deviation, then you have to think of something else. So now you can see here, this part you also have covered. Right, okay, good. So now only this part is here left. Let us try to understand. Well, these are the significant quotes that different values of alpha. So that is also done. Now we move a little bit more, and then we try to understand, and then I will come back again whatever is left. So this is the screenshot of, if you try to do it yourself on the our software, it will come like this. So now exactly here I am trying to show you these things in more detail only, which I have just explained you on the screen itself. So if you try to see here, this is here n equal to 20, k equal to 4, and if you try to take it here, say h naught beta 0 equal to 0 versus h1 beta 1 equal to 0, then this is the line which is corresponding to this hypothesis, right? And I have just shown you in more detail that how these values are actually obtained. That is more important as a scientist for you to understand. I'm not bothered that you should know how to multiply a complicated matrix or something like this, right? But you should know that which tool's value is going to be here. So you can see here, if you want to obtain this value here, you can just substitute all these values and you can get it. Right, so means I was just trying to give you a more lucid presentation, but I'm sure that if you have understood there are no question, then it is simply the repetition of the same thing which I just explained you. Right, so similarly, if you come to the second one, this is conducting the result for the H0 beta 1 equal to 0. And similarly, if you come to this third row, this is conducting the test of hypothesis H0 beta 2 equal to 0. And if you come to the last row, this is conducting the test of hypothesis for H0 beta 3 equal to 0. Right, so it is not difficult. Now, after this, there's another thing that we also try to obtain the confidence interval. I believe that you have an idea of point estimate and confidence interval estimate. That means whenever we are trying to estimate a parameter from the population, I have two options. Either I can estimate it in the form of a point or an interval. That is the same thing if I ask you, well, from your college to the your home, how much time do you take every day in coming to your college? So if you say, no, I take it 25 minutes, that is the first statement. And second statement is that, okay, I take between 20 and 30 minutes. So what you have done, you have taken the observations of the last couple of days, that how much time you have taken, and then you have found out the arithmetic mean, so that will give the value of the time at a point. But then you also want to know these values in the form of an interval, so 25 to 30. So this 25 to 30 is the interval estimation. So we can also obtain here the confidence interval estimates for these unknown parameters, because the parameters are unknown. We are simply trying to estimate it. So that is our choice, whether we want to use it a point estimate or an interval estimate, etc. Right. So The question is how to find out those confidence intervals. So I am simply giving, without any proof, I am giving you here an expression, right? And these things can be obtained in this R software for this regression analysis directly. For example, if you use this command here, confint, CONFINT, and then you write this formula here, and then you have to give it the confidence level. I say this 95% confidence interval. You can see here you are getting here these two values. So you can see here, this is the, means you are trying to say that your intercept term will be lying between 6.58 and 10.95. Your beta 1, that is your, which is estimated by B0, will lie between 1.92 and 2.06. And similarly for here, this, say here, if you try to say here, the value of beta 2, which is estimated by B2, that will lie between 3.56 and 4.27. And similarly here, this beta 3, that is estimated by B3, will lie between 5.95 and 6.25. And if you try to obtain this manually also, you can do, but then why should I do the calculation when I have a software? The main thing is I have to understand how these values are obtained. So this is how you can obtain the confidence interval also. So that will give you a better idea that when you are trying to estimate your unknown parameters, now you know that what is the possible interval in which this value can lie. Right, so this is the screenshot of the same outcome. Now, the other question comes here. Once you have obtained the model, then how do you know whether the model which you have obtained is good or bad? So we have one criteria here, which is called here as a coefficient of determination. So obviously the basic question comes here, how can you decide that whether something is good or bad? Suppose, for example, in my class, Miss, I say, okay, if somebody has got more than 90% marks, then the student is good. So similarly, when you are trying to take the two types of variable which are interrelated to each other, and you are assuming a linear relationship. So obviously, if you have here a model like this, if I try to draw a picture here, like this one, and suppose the points are lying here like this, and there's another model in which same model in which the data is like this. So obviously here the points are very, very close to the fitted line, and here the points are quite away from the fitted line. So that means in this case, I can say that the model is better fitted. Right. So if you try to see what is the feature I'm going to use, suppose if I say here, suppose all the points are exactly lying on this line, then this is possibly the perfect fit. That whatever your model is saying, that is happening. I mean, that is the same thing. Means nowadays, every day, people are trying to forecast that how many number of COVID cases are going to be there after a week, and when it is going to finish, etc., etc. What is that? If their model and the number of COVID cases they are matching, that means their model is good. So now here the question is, how are you going to take a call whether your model is good or bad? So one option here is that I can find out the correlation coefficient. So when we are trying to find out the correlation coefficient between y and x, that is the Karl Pearson correlation coefficient, that gives us an idea about the degree of linear relationship between x and y. And now we have here one y and here x1, x2, means more than one variable. So if I try to find out the correlation coefficient between y and a group of independent variable, then this correlation coefficient is called as multiple correlation coefficient. And this is called as here as a, if you try to take the square of this multiple correlation coefficient, this is called r square, or this is called as coefficient of determination. So this value of r square gives us an idea that whether the model which you have obtained on the basis of given set of data is really good or bad. Right. So one very important thing which thousands and millions of people make such blunder. The value of r square, which I'm going to define here, this is valid only when there is an intercept term in the model, because in many situations there can be two types of model that you would like to fit. One is model with intercept term and model without intercept term. because it depends that whether you want to have an interceptum in the model or not. Why? Because interceptum is the average value of the y when all x's are 0. So if I take a simple example of say this fan and electricity, means if you just put your electricity at 0 level, that means you switch off the fan, then the fan cannot move, right? Whereas in the agricultural field, if you don't give any fertilizer, don't give any irrigation, with the natural things also, you will get some crop. So in that case, you would like to have the interceptum in the model, whereas in the first case, you would not like to have the interceptum in the model. Right. So this is the thing. So this coefficient of determination is valid only when there is an interceptor in the model. Right. So I consider here this model in which I am considering the interceptor, and this R square is defined here like this. Right. That, so you can see here this depends only on the value of y and x. So you can compute this value, and this value lies between 0 and 1. There is no issue. Right. Okay. So now the question is this: what this R square does? So R square measures the explanatory power of the model, which actually reflects the goodness of fit of the model, and it reflects the adequacy in the sense that how good are your explanatory variable in explaining the variation in y, because you are trying to take different types of variables, and your objective is that you want to understand that whatsoever is happening in y, that should be explainable through the values of x's, right? So, and in simple words, if I say this R square lies between 0 and 1, so R square equal to 0 means we will indicate the model is extremely bad. That is the poorest model. And similarly, if you take R square equal to 1, this will indicate that the model is actually the best model. But this model is only with the God. And if you try to get here any other value of R square between 0 and 1, say 0.95, then in general words, I can say it would indicate that the 95% of the variation in y is being explained by the choice of variable that we have considered, and in general this model is 95% good. Similarly, if you take any other value of R square, possibly that will give you an idea that how good is the model, right? But this R square has a problem that the value of R square increases as the number of independent variables increase. So the drawback is that even if you try to add a garbage variable, the R square will increase, and that will indicate that as if your model is getting better and better, but that will be a wrong statement. Right. So in order to take care of this problem, people try to modify this R square, and they define the adjusted R square. And this adjusted R square has one issue, that it doesn't increase as means significantly when the number of variables are changed. Right. And the third thing is this: what you have to keep in mind, that if the intercept term is absent in the model, so sometimes this R square can be negative also. So you have to think this is a square quantity. It should always be positive, but that may become negative. So, right. So in case so, and the constant term is absent means the model is passing through origin. So for that, some ad hoc measures have been given in the literature, but they are not very dependable, honestly speaking. So this adjusted R square is defined here by like this quantity you can see. So it is some modification in the value of R square. So how it is obtained, that is not your job, but it is for your information that this is called as adjusted R square, and it is indicated by R bar square, right? So now let us try to find out these things in the given set of data. So we take here the same data, and we try to here use the same formula here, summary. So you remember here that we already have covered this part, this part, this part, this part, up to here. This part we have covered. Now, if you see in the bottom, there is a line here, multiple R squared, and then here is say adjusted R squared. So you can see here this multiple R squared here is 0.995, and this adjusted R square here is 0.9994. Right. So this is giving you that, okay, in this case, the value of R square is 99.95%. Yeah, well, I have taken this data artificially, so that is why it is coming out to be so high. In practice, usually it will not come, because if you have model with this accuracy, means this model is close to the model of the God. But that was only for the sake of illustration only, right? And then the value of your adjusted R square, that it comes over here, right? So this is how you have obtained this value by this formula. So you don't worry for these things. Right. And if you simply want to obtain the value of your R square, that you can obtain here directly using this command, summary and then dollar and then R dot square, or this summary dollar adjust adj dot R dot square. Right. So this is how you have to do here. The only thing which is now here left is only one thing, that I had given you here, the value of sigma square. Right, do you remember we had made this assumption in the beginning? I will show you. Yes. This, and the value of the sigma square can be obtained on the basis of given sample of data. So where in this outcome you are going to obtain it? I will try to show you here. If you try to uh, see here, okay, let me try to same which is more clear. Yes. No, sorry. Yes. Who can come here? This is the same outcome. Means I have copied pasted at several places. If you try to look at this quantity, residual standard error, this is the quantity of value of square root of sigma square hat. So whatever sigma square hat I have given you, we just try to take its positive square root. That is the residual standard error. So this is the value of here sigma square. Now there is here one more last value here, f stat 6. This is about the analysis of variance, but surely I think it will become too much for you if I take the ANOVA table also. But this analysis of variance is only h naught, say beta 2 equal to beta 3 equal to beta 4, this test of hypothesis. So now you can see here, I started my lecture one with this slide only. And if you try to come here, I will try to show you now here, but let us try to understand whether we have covered all the things or not, and now whether you can really interpret all these results from the software or not once again. So you can see here, this is what we have understood. This is the command. This is, we have understood what is this thing. We have understood this estimates 1, 2, 3, 4. It looks very nice when you have to cut, when you have covered these many things. Right, now you also have understood what is this line. You also have understood this line. And now you also have, at least I have not explained you, but I am telling you, this is only the test of hypothesis for H0 beta 2 equal to beta 3 equal to beta 4. And you can see here this p value is very small. So means you are simply trying to say that H0 say beta 2 equal to beta 3 equal to beta 4 equal to 0 is rejected. Well, obviously means here all the values are important. They are not close to 0. So because of the simultaneous equality of all the parameters. Right. So now we have covered all the things. So now let me come to an end to this lecture, and I hope